understand these things such that you don't have to be intimidated by the complexity, and instead you can embrace it and start to make meaningful predictions about it. And I'm going to talk about one of those ways today. What I want to talk about is a thing called emergence. And emergence is the idea that you can take the small parts in a system and look at the interactions between them and put them in a simulated environment and watch the complexity of that system emerge spontaneously rather than building it in explicitly. Now, that's a little bit abstract, and even though we're at TEDx, that's still a little bit abstract. So I'm going to give you an example of something that's hopefully familiar to everybody. This is a flock of birds, right? Hopefully everybody's seen a big one of these, right? And when you see it, it moves very organically, and it's a complex system. It's made up of a lot of individual parts. Now, if we're going to take a traditional modeling approach to making a prediction model about how a flock of birds behaves, we would probably do something that involves making an algorithm that says where each bird in the flock is supposed to be relative to every other bird at any given point in time, and then we'd build in some additional algorithms that talk about things like food, talk about avoiding predators and other behaviors. But 9 times out of 10, if you build your model this way, it's going to eventually either end up looking really robotic, not lifelike like we want it to look, or it's going to be confronted by a scenario that's not programmed in there, and it's going to crash. It's going to crash your model, crash your computer, right? So instead, what I propose is to build this complex system differently, right? Let's build it instead based only on the interactions between the individual parts in the system and let that complexity emerge. What about if I told you I only want 3 rules for every individual bird in the flock, right? First rule is going to be don't hit your friends. That's not nice. You'll get exiled from the bird flock if you do too much of that, right? Second rule is fly the same direction as everybody that's kind of in your cone of vision, because they all probably know where they're going. Third rule is don't be the lone straggler in the closest group of guys waiting to get picked off by a predator. There's safety in numbers. Okay? If I put all of these together in a simulated flock, in a simulated environment, I get these. The solution to that is the solution to a famous emergence problem from the 1970s called Boids, B-O-I-D-S, where there were a bunch of biological researchers struggling to learn about complex biological systems. Now, those 3 rules I just showed you are the basis for all swarm and insect logic that's used today in every application, from computers to the way that drones fly around for our military, right? And you might say that, hey, Joe, a flock of birds is one thing, right? But humans are infinitely more complex. And they are. That's very true. But we don't need to be intimidated by that. That's actually a good thing for emergence because it thrives off of the interactions in a system. And one thing I know is if you get a group of people, they're going to interact with each other, even if it's not always in obvious ways, right? So what you can do is take those same 3 rules that I just told you about and start to apply them to systems of humans, right? You can start to look at things like traffic patterns and traffic congestion. Start to look at spontaneous human organization into systems like governments, coalitions, political parties, insurgencies. Start to look at the movement of crowds and pedestrians, the way they flow, the movement of riots. Start to look at the dissemination of information on social networks on the internet. Look at the outbreak of disease and the way it spreads through a population. You can look at the spontaneous growth and organization of cities, of urban sprawl, and the formation of slums. You can bring it all the way back to the economic herding behavior and irrationality that was at the very core of the last financial meltdown that we just experienced. Now, these are simplifications of the rules that you use to actually try and simulate these things, but you can begin to see the power in thinking this way. It's a power in terms of adaptability, of using small to become big, and using a minimum number of rules to do so. This is a quotation that I really like, that I think sort of summarizes the direction that this sort of thinking can take us. It's very much a place of convergence, synthesis. Using this type of thinking, a lot of disciplines are going to start to mesh and come together. Art, science, mathematics, physics, engineering, because you can begin to solve the hard problems in every one of those disciplines using the same way of thinking about things if you use emergent systems. But it's not going to be easy for us. See, our brains are hardwired instinctively to respond to complex systems in one of two ways. We either dive deep when confronted with a complex system to the part that's most familiar to us, the part that makes us feel at ease, that we feel we understand the best. And we tend to ignore the rest of the system, which may actually have important elements in it that help you understand that system. Or the other way that we go is we try to take it all in at once, try to understand the whole system at one time. But it's too much information, and we can't. So we start to make up rules and assumptions and introduce bias into the way that we understand the system. Now, both of these things on their own can lead to bad predictions. But increasingly, the world is going to challenge us in new ways as well, because things are getting faster and more complex at a rate that we've never seen before, right? Data is getting bigger. Information is flowing faster. People are getting more and more connected. And these types of networks of complex systems of people spring up overnight and disappear just as quickly. How can you even begin to understand something like that unless you have a better way of looking at it? You know, the real danger, especially for those of us that are technical folks, is that the solutions that we come up with to problems are going to be obsolete by the time we're ready to deploy them, right? Let me put that differently. It's not going to be enough in the future to just solve problems. We're going to have to recreate the system that led to the problem in the first place and understand it if we want our solution to have any chance of succeeding. So really put in context where we're at today, I want you to imagine a dog. It's a dog you're going to raise as a pet, right? And we generally have a pretty good understanding of the behavior that dogs have, right? We know based on our observations of dogs throughout history, there are certain things they're not going to do, right? Dog is not going to talk, right? And we use those observations and about the limitations of behavior of dogs when we interact with them, when we try to train them and try to understand them. Now I want you to imagine a child, right? A child's significantly more complicated than a dog, right? And the spectrum of behavior that a child can have is significantly wider than a dog, right? We think we generally know what kids are going to do, but any parent out here will tell you every now and then kids will do something completely unexpected that we didn't think that they were capable of, right? So on the whole, though, we still think we have a pretty good idea of how to raise children, while at the same time acknowledging that from time to time they're going to do things that are completely outside the bounds of what we can imagine they're capable of, right? Now I want you to imagine a hypothetical child, right? This child's the same as any other child, except that every 30 minutes, this child takes on the personality and intelligence level of a random child somewhere in the world, right? So for the first half hour, the child might be completely normal, right? Second half hour, the child might have ADHD. Third half hour, the child might have emotional problems. Fourth half hour, the child may be completely unresponsive. In the last half hour, the child might have a genius intellect, right? How do you even begin to bound what kind of behavior you would expect from that child? So the dog in this example is like the complex systems of the last century, right? The ones we're used to, the stock market of the mid-1900s, for example. We have a really good idea, even though there's uncertainty in there, of where that uncertainty is bounded. We think that the complex systems of today are like that middle child, but really, they're already becoming, and will increasingly become, much like that last child, right? And how would you even begin to understand that last child with traditional child psychology and traditional ways of raising that child, right? I would contend that the only way that you can start to understand that child, start to make predictions about what they're going to do, is if you live in the moment, right? If you understand the small-scale behavior and the low-level interactions between you and that child without worrying about things like what their eventual career is going to be or where they're going to go to college. This is the way in which we can begin to understand the complex systems of our world. This is the way we can begin to predict the things that are going to emerge from them. Thank you.